Hi guys, so in this video I'm going to basically present to you a question which is a part of what is called the Biggs theorem. So Biggs theorem is a theorem in calculus that essentially compares the rate of growth of different kinds of functions. So for example, it says that the exponential function always grows faster than any polynomial and so on and so forth. So this is just one part of the Biggs theorem, which says that the logarithm function, or in other words, the ln function over here, grows much slower than any polynomial. So in this case, this is basically the statement in front of you is basically just a rigorous version of that statement. So it says let f and g be functions defined on the interval from 1 to infinity, and we are assuming that these functions are always positive. And we say that f grows much slower than g. In other words, what we can say is that as x approaches infinity, the slope of the tangent line of f is much smaller than the slope of the tangent line of g. So f grows much slower than g if and only if limit as x approaches infinity of f of x divided by g of x is equal to 0. So this is just the definitional perspective. And then what we need to show is that for any natural number n and any delta greater than 0, we need to show that ln of x to the power of n grows much slower than x to the power of delta. So in other words, what we need to show is that for any n in any natural number n and any delta greater than 0, limit as x approaches infinity of ln of x to the power of n divided by x to the power of delta is equal to 0. And of course, if this is true, we know that ln of x to the power of n grows much slower than x to the power of delta based on this definition of what it means for a function to grow much slower than some other function. So at this point, I would ask you to pause the videos and see if you can solve this question on your own. Prove that ln of x to the power of n for any natural number n and any delta greater than 0 grows much slower than the function x to the power of delta. So by now, I hope you've attempted this question on your own. There are several different ways to prove this theorem, especially because I've limited n to be a natural number. In this video, I'm actually going to present a proof that works even if n is a real number. The only benefit of having n as a natural number is that you can then go ahead and write a proof by induction, but that is, I personally believe that's unnecessarily long. But once again, I mean, the set of natural numbers is a subset of the set of real numbers. So if you prove anything for every number in the set of real numbers, then that must also be true for the set of natural numbers, because the set of natural numbers is a subset of the set of real numbers. So in this case, I'm going to say, here's how I'm going to begin the proof. I'm going to say let n be any real number. And I'm going to say let delta be any real number that's greater than 0. And then I want to show that limit as x approaches infinity of ln of x to the power of n divided by x to the power of delta is greater than 0. Is equal to 0. Now, before I actually, explicitly write out the proof for this theorem, I'm going to prove a lemma. So what is a lemma? So a lemma is basically a proof inside a proof. It's typically written, it's essentially something that is not trivial and that needs to be proven, but the proof of that thing itself will be used in order to write out the proof for the general theorem. So in this case, the lemma I'm going to use is, I'm going to say my lemma is as follows. I'm going to prove for any positive real number, for any, let's say I'm gonna say, let's say lambda, for any lambda greater than 0, so for any positive real number, the following is true. Limit as x approaches infinity of ln of x divided by x to the power of lambda is equal to 0. So you'll see why this helps out, because this is something that is very easy to prove. So I'm going to say let the proof for this lemma is let delta be greater than 0. Then limit as x approaches infinity of ln of x divided by x to the power of lambda is the same. If I apply the L'Hopital's rule over here, I'm going to get this is the same thing as limit as x approaches infinity of the derivative of the numerator is 1 over x, and the derivative of the denominator is lambda times x to the power of lambda minus 1. And if I just simplify this, I'm going to get this is the same thing as limit as x approaches infinity of 1 divided by lambda times x to the power of lambda. And since lambda is something that is positive, as x approaches infinity, x to the power of lambda also approaches infinity, and thus essentially you get 1 over infinity, which is just 0. So clearly this holds. For any delta or for any lambda greater than 0, limit as x approaches infinity of ln of x divided by x to the power of lambda is equal to 0. And this is what I'm going to use. So I'm going to say thus, I've shown that limit as x approaches infinity of ln of x divided by x to the power of lambda is equal to 0 as needed. And this is my lemma. So now I'm going to use this lemma to prove that limit as x approaches infinity of ln of x to the power of n divided by x to the power of delta is equal to 0, where n is any real number and delta is any positive real number. So now this is actually going to be pretty simple. I'm going to say note. Okay, so limit as x approaches infinity of ln of x to the power of n divided by x to the power of delta. Now this is the same thing as limit as x approaches infinity of ln of x divided by x to the power of delta over n whole power n. I mean, if you just distribute n in the numerator and the denominator, you're just going to get ln of x to the power of n divided by x to the power of delta once again. Now, I'm going to make a claim over here. I'm going to say that this is equal to limit as x approaches infinity of ln of x divided by x to the power of delta over n whole power n. But this needs to be justified, and this manipulation is only justified if this function ln of x divided by x to the power of delta over n is continuous as x approaches infinity. And that is of course true. The numerator is continuous for all x that are greater than 0, and then the denominator is continuous for any real number, and thus the entire function is continuous for any real number that is greater than 0. I mean, in this case, if the denominator is equal to 0 only when x is equal to 0, so the only discontinuity occurs at 0, and this function is continuous everywhere else. In particular, I only want it to be continuous on the interval of 1 to infinity, or basically any cutoff till infinity. So it needs to be continuous on, let's say, a to infinity, where a is any real number. So as long as it's continuous as x approaches infinity, this manipulation is justified. So I can say this is true as the function ln of x divided by x to the power of delta over n is continuous on the interval of 1 to infinity. I know that limit as x approaches infinity of ln of x divided by x to the power of delta over n to the power of n is equal to limit as x approaches infinity of ln of x divided by x to the power of delta over n whole power n. And this is true because of the by the limit law of composition. So if you don't know what the limit law of composition is, I'm probably going to leave a link down below in the description box where one of my professors actually explains the limit law of composition, and I believe it's explained really, really well over there. So you can use that to understand what the limit law of composition is. Okay, so once you reach this point, now you only need to realize that there are 3 possible cases. So now there are three possible cases. So let's begin with case 1. And case 1 is when n is something that is greater than 0. Okay, so let's see what happens when n is greater than 0. If n is greater than 0, then of course limit as x approaches infinity of ln of x to the power of n divided by x to the power of delta over n is, just x to the power of delta is equal to limit as x approaches infinity of ln of x divided by x to the power of delta over n whole power n. This basically just follows from right here. And of course, this is just equal to 0 to the power of n. And why is this equal to 0 to the power of n? Because remember that both delta and n are positive real numbers. So delta over n is also a positive real number. So over here, delta over n is a positive real number. And by the lemma that I proved, limit as x approaches infinity of ln of x divided by x to the power of any positive real number is just 0. So this limit over here is effectively just 0, and I get 0 to the power of n, where n is once again a positive real number, and 0 to the power of any positive real number is simply 0. So in this case, I've proved that limit as x approaches infinity of ln of x to the power of n divided by x to the power of delta is 0. Now there's another case. There's a case 2, and that is when n is equal to 0. Now, if that is the case, then limit as x approaches infinity of ln of x to the power of n divided by x to the power of delta is equal to limit as x approaches infinity. Now, since n is equal to 0, ln of x to the power of n is the same thing as ln of x to the power of 0, and anything to the power of 0 is just 1. So we're just going to get 1 in the numerator and an x to the power of delta in the denominator. But then again, as delta is a positive real number by assumption, then x to the power, as x approaches infinity, x to the power of delta also approaches infinity. So you effectively get 1 divided by infinity, which is 0 again. So in both cases, I proved that limit as x approaches infinity of ln of x to the power of n divided by x to the power of delta is 0. Now there's also a third case. And this third case is what happens when n is less than 0. So this is once again the same thing, limit as x approaches infinity of ln of x to the power of n divided by x to the power of delta. Now this is the same thing as limit as x approaches infinity of 1 divided by x to the power of delta times ln of x to the power of negative n. Now this is where you have to be a little bit careful. Notice that as x approaches infinity, x to the power of delta approaches infinity as well. And as x approaches infinity, ln of x to the power of negative n also approaches infinity. This is simply because negative n is a positive real number because, well, n was less than 0. So I could maybe even say that n is less than 0, which implies that negative n is greater than 0. So in other words, as x approaches infinity, x to the power of delta approaches infinity, and ln of x to the power of negative n also approaches infinity. Thus, effectively, you get 1 divided by infinity times infinity, which is essentially just 1 over infinity, which once again is simply 0. Hence, and now I just need to write my conclusion. I would say hence, in all cases, limit as x approaches infinity of ln of x to the power of n divided by x to the power of delta is equal to 0. And that's the proof. Now, one thing that I would like to emphasize over here, if you go all the way back up, the question essentially just asks us to prove that the following property is true for any natural number n. So if you did not want to prove this theorem for every real number, then you actually did not have to consider the last two cases. You did not have to deal with case 2 and case 3, assuming, of course, you are going with the idea that 0 is not a natural number. There's a lot of controversy around that. Some schools or even some universities will keep 0 in the set of natural numbers and some won't. But assuming you do not, keep 0 in the set of natural numbers, your proof would actually end once you've proved case 1. Because, well, natural numbers are by definition positive, And if you're proving that something is true for every positive real number, it must also be true for every natural number. So if you only wanted to prove this theorem for the set of natural numbers, you can actually use the same process up until case 1 and then end your proof over there. You can basically just write down your very last statement as you can say that since I've proven the theorem for every positive real number, and since the set of natural numbers is a subset of the set of real numbers, the the theorem also holds true for the set of all natural numbers, or for the set of natural numbers. Okay, but if you want to go ahead and if you want to prove this theorem for any real number, then you need to actually recognize that there are two other cases. There's a case 2 and there's a case 3 as well, where n is negative and then where n is equal to 0. And then you also need to solve for those two cases separately. And that is what I've done over here. So just to show you a little bit about why this theorem, you should find this theorem to be a little bit surprising. And the reason being, for example, if you were asked to compute this limit as x approaches infinity of ln of x to the power of, let's say 10,000. It could even be a billion, a trillion, doesn't matter. And then you say divide this by x to the power of 1 divided by 10,000. The answer over here is actually 0. Although, I mean, at first sight, you might think what ln of x has been raised to the power of 10,000. Or for that matter, even, you could, doesn't matter how many zeros you add. I mean, even this equality is still true. So at first sight, you might think, okay, what's happening over here? Ln of x, it's ln of x to the power of like a billion or a trillion. And then I'm just dividing it by x to the power of 1 divided by 10,000. And as x approaches infinity, this is still 0. So at first sight, this might seem like something that's very, very weird, but the proof actually, or I mean, even at first sight, if you ask this question to someone who has not studied this proof, or maybe someone who only knows the L'Hopital's rule at best, even they would say, well, maybe the answer is not 0, maybe the answer is something else. But someone who's seen this proof or who knows how logarithms and polynomials work, they actually know that this limit is 0. It is kind of surprising. I mean, you wouldn't expect this limit to be 0 because, well, the numerator is just a very, very huge number. Even if you just plug in x equals 2, the numerator is just way larger than the denominator. But once again, as x approaches infinity, the denominator does grow much faster than the numerator. And yep, that's pretty much it for this video. I hope you enjoyed the video. And yep, that was the proof that this was the proof for the theorem that the logarithm function grows much slower than the polynomial function. And yep, that's it. I hope you enjoyed the video, and I'll see you in the next video.